Greetings, welcome back. With the 3n+1 problem, numbers seem to trend downwards, but they bounce up and down a lot. So even if you believe a number has to trend downwards, it might accidentally hit itself while it's bouncing around, causing a loop. So how do we find such a loop or prove that none exist? If there's a loop, it'll consist of some sequence of operations like this. Yellow stands for 3n+1 over 2, blue stands for n over 2. If we start with a certain number m and apply those operations, we'll get some number out. If it's the same number m, then it loops back on itself instead of hitting 1. So given an operation sequence, we can actually solve for the m that has that property. There's only one. In this case, m is 11 point something. It's not a whole number, so even though we have a loop, it's not a counterexample to the 3n+1 conjecture. Actually, we already knew this wasn't a loop because any whole numbered loop is going to have k greater than 11 million operations. So imagine we keep adding billions of yellow and blue blocks. Will we eventually hit on some operation sequence that maps some huge whole number m back onto itself? Nobody knows. So suppose we restrict ourselves to operation sequences like this, where we go up x times and then down k minus x times. That's a circuit loop. Turns out there's a very simple formula for m, and if we keep adding yellow and blue blocks, we want to know if m will ever be a whole number. So let's assume it is a whole number for some x and k. Then this is also a whole number. We just added 1. And simplifying, this is also a whole number. And this is also. So at this point we can cross out the 2 to the x because the denominator isn't divisible by 2 or 3. But this is not a whole number, it's less than 1. That's because Baker and Ellison told us that the denominator is greater than 2.5 to the x, and in this case the numerator is less than 1.5 to the x. Why is that? Informally, it's because the yellow operations multiply by 3/2 each, and the blue operations divide by 2 each. So for m to return to its original vicinity, this product needs to be about 1. So you need more yellows than blues. But this kind of glosses over the +1 part. So formally, we can just require that m be greater than 1. And in that case, we can do some simple algebra to come to the same conclusion. Okay, even if we add billions of yellow and blocks here and blue blocks here, that means we'll never get a 3n+1 loop. And we saw a similar result considering sequences like this, where m works out to 5 times this, and if m were a whole number, then this would be 2. We just added 5 to it, and so would this. And again, the numerator is too small because if m is greater than 1, if it's going to be greater than 1, then the numerator is less than 1.2 to the x. Okay, how about this sequence? We didn't look at this. This is up, down, etc. If you work it out, m is 4 to the x minus 3 to the x over 2 to the k minus 3 to the x. Well, here if we set k to 2x, then m is a whole number. It's 1. But, this is the old 1, 2, 1, 2 loop. But if k is any bigger, then m will obviously be less than 1, and so we won't get a loop. So just a note that we got to be careful. When m is small, you don't need more yellows than blues, but of course we only care about when m is big. So can we rule out loops for all kinds of other operation sequences? Ones with patterns like these, patternless sequences, or like this one or this one. Well, this one's what we call the high loop, arrangement of k operations that leads to a loop with a very large bottom member compared to the other loops. If there's a loop with tens of millions of members, it's probably going to look something like this. It interleaves up, up, down operations with up, down operations. But the interleaving is kind of patternless. It's related to the digits of an irrational number, log of 3. So as a baby step, let's arrange all the up, up, downs, a of them, before all the up, downs, b of them. Now we can write a general expression for m, which turns out to be pretty hairy, but okay. If this is a whole number, then so is this, and eventually, amazingly, is this. So with a little effort, we can also show that b is small, so it's got to be less than 17% of x. That means 4 to the x is less than 1.27 to the x, so m is never a whole number after all. It's less than 1. So there's no 3n+1 counterexample loop that looks like this, no matter how big a and b get. So how is this related to the high loop? Well, if I swap these two operations and these two operations, then I've got this apparently patternless high loop. Each swap changes m's numerator just a little bit. It adds 3 times some power of 2. But I don't know if that change can suddenly cause m to be a whole number. So that's something to look into. Okay, hope you liked this episode, and see you next time.